Hi, I'm Sivesh Khatan. This summer, I have been working under Dr. John M. Dolan and his postdoc Dr. Shin Lin in the Ergo Air Center for Autonomous Vehicles Research. My project for RIS is solving common road motion planning benchmarks using CILQR. Motion planning in dynamic environments is a critical component for self-driving car technology. Many solutions have been proposed for motion planning. However, most of the solutions which have been proposed previously have been tested only in simple scenarios like car following or lane changing. In our work, we demonstrate how CILQR, which is an optimization based algorithm coupled with a high level path planner and a prediction framework, can be used to solve motion planning for self driving in generic scenarios. To demonstrate the effectiveness of our framework in real-world environment, we test its performance using common road benchmark scenarios. These are a collection of composable benchmarks for motion planning on road which have been created using real-world traffic datasets like the ngSim dataset. Common road consists of different planning problems, and for each planning problem, it provides a traffic scenario, a goal region, and a lanelet network describing the road network architecture. The interface also provides the updated state of the ego vehicle and the dynamic obstacles at every time step. A planning problem is considered solved when the planner is able to generate a collision-free trajectory, avoiding the road boundary and being kinematically feasible according to the vehicle model considered. The final state has to be completely within the goal region as well. This is an overview of the proposed solution for solving the benchmarks. It works in a receding horizon framework. For each planning step, the high-level route planner generates a series of lanelets to traverse in order to reach the goal region specified in the planning problem. Concurrently, the prediction framework also generates future trajectory predictions of the dynamic obstacles. The motion planner then uses the reference lanelets, the predicted dynamic obstacles, and the road boundary as constraints to generate a kinematically feasible trajectory for the car's controller starting from the ego vehicle's instantaneous state. The common roads route planner has been used to generate the reference path. The planner uses an A-star search over the lanelet network's directed graph and gives a path containing a sequence of lanelets which lead to the goal region. This path, however, might be kinematically infeasible and it also can lead to collisions which need to be dealt by the motion planner. Next is a prediction framework. This has been adopted from our previous work, Spotlight. We initially get the perception data, that is, the state of the environment, which includes the position and velocity of the surrounding vehicles. Based on this perception data, we predict the future trajectory of the surrounding vehicles using a short term and a long term prediction. Reachability analysis is used for the short term prediction, while for the long term prediction, we use a recursive least squares filter. These predictions are then used in the planning layer, which is the constrained iterative linear quadratic regulator, or the CILQR. It is an optimization based planner which incorporates the deviation from the reference, the cost of applying high acceleration and steering, and obstacles in the cost function to generate the trajectory for the ego vehicle. The road boundary constraints are non-convex, thus they are differently incorporated. The boundary of the roads are sampled and these sample points are set as tiny obstacles for CILQR. This makes sure that the trajectory does not violate the boundary constraints. Also, since there are time constraints within which the goal has to be reached, it is incorporated implicitly into the position reference points. These are some of the example scenarios results. The proposed solution is able to solve a multitude of scenarios ranging from turns, junctions, urban traffic, etc. Further, we aim to extend our approach to more complex dynamic models for the ego vehicle and also improve the real-time performance of the whole framework. I would like to thank my mentors, Dr. Sheen Lin and Dr. John M. Dolan, for guiding me in this research project, Ms. Rachel Bursin for co-directing this program, and the whole RISC community and the sponsors for providing us with this amazing experience.